Alright, this video, I'm going to go over a method called the Gauss-Jordan method. And this is essentially if you wanted to solve a system of equations by hand, using these augmented matrices, the process that you would go about solving these things by hand. This is a purely optional video, so if you wanted to skip it right now, go right ahead. We're going to be doing this same sort of stuff on the calculator. The only reason I'm doing it and putting it in here is so if you want to watch, you can get more of an appreciation for what's happening behind the scenes. I'm always kind of amused by when people have a bunch of equations, x squared plus y squared, and then they have some big thing happen, and there's a big explosion, and then they get a nice happy result out of it. Well, okay, maybe equals mc squared. I'm guessing he didn't have a nice explosion to have that result happen, but I'm not a big fan of just saying, oh, trust me, this is how it works. So let's look to see how you would do this by hand. If you want to do these things by hand and submit that work, that would certainly work for you. I don't think it's worth your time, though, because it's really easy to make a lot of mistakes, or really easy to make mistakes because there's a lot of steps here. All right, so in any case, getting on with the actual method. Essentially, there's 3 different legal moves that we can do. I'm going to treat this kind of like a game. We're starting out in this position, and we can move things around. We can interchange stuff. We can do things to these rows, and ultimately, our aim is to get the ones along the diagonal, zeros elsewhere, and then whatever ends up being over on the right side of this. So I don't know what's going to end up over there, but we want the ones there and the zeros there. Alright, so the legal moves that you can do is you can interchange 2 rows. So right here, as an example, you can interchange rows 1 and 2. So that's what I'm going to do. This gives us -2, -6, -10, -12 as the first row, 0, 1, 2, 3 as the second row, and 2, 1, -2, -5 as the third row. The reason this one makes sense, the reason it is a legal move, is each of these are equations, and the reason they're listed out in this order is only, well, that's pretty arbitrary. That's just the order the equations are listed. You can rearrange the equations, and it clearly doesn't change what point would satisfy all 3 of those equations. Alright, so let's take that one, and another thing we can do is we can multiply a row by any non-zero number. And this is generally what it would look like if you're doing that. So this is saying take the number -1/2, multiply it by row 1, and assign it to row 1. So that's what I'm going to do here. I'm going to take -1/2 times this row, times each of the values in this row, and assign it back into place. Nothing else is going to change, though, so let me just take a second and copy the other 2 rows. Alright, there we go. So this first row, multiply by -1/2, or the easier way of thinking of that is dividing by -2. -2 divided by -2 is 1. This divided by -2 is 3. -10 divided by -2 is 5. -12 divided by -2 is 6. So there you go. That's the second move we can do. The reason we can do that one, again, these are just representing equations, and when we have an equation, I can multiply through the entire equation, both sides of the equation, by whatever number I'd like. In this case, I'm multiplying through this side of the equation by -1/2, and this side of the equation by -1/2. So, there's nothing fancy going on here. The last thing we can do is we can add one multiple of row to another row. This one might be a little bit tricky. If you did the elimination method, back when you're dealing with 2-dimensional variables, so if you had something like 3x plus y equals 6 and 3x minus y equals 2, okay, that's a bad example, let me not do 3x on both of those, 3x and, I don't know, 4x. If these 2 are your equations, before you would have seen it as adding the 2 equations vertically. Really what you're doing is you're taking this side of the equation and adding it over there, taking this side of the equation and adding it over there, and we get something nice. We get, 7x equals 8. Well, whatever. In any case, that is where you may have seen something similar to this before. What we're doing is we're going to take a multiple of one row and add it to another row. So we're going to take a multiple of this equation, this row, and add it to row 3. That's what this is saying. Take negative 2 times row 1, times each of the values in row 1, and assign those values back, and add it to row 3, then assign those values back to row 3. You'll notice I'm not changing either of the first two rows, so I'm just going to copy those down first. But now what I'm going to do is I'm going to do negative 2 times this value and add it to the value, that corresponding corresponding value in row 3. So negative 2 plus 2 is 0. Here we do negative 2 times 3, which is negative 6. Add that to 1, we get negative 5. Here we do negative 2 times 5, which gives us negative 10. Add that to this, we get negative 12. Here we do negative 2 times this is a negative 12. We add it to here, we get, what, negative 17? So this is kind of a combination of multiplying something and then doing the adding one side of the equation to one side, the other side of the equation to the other side that I kind of was talking about up here with the elimination method. So that's the justification for why we can do that one. Now, in these first 3 steps, you may have noticed something happening. I created it, we started out with our matrix that looked like this, 0, negative 2, 2 in that first column. In this column, it now says 1, 0, 0. What we say is that this is kind of how we would proceed from here. Is we would continue this process. We would start saying, what we did is we established a 1 up here, and then we used that 1 to get rid of all the values that are below it, to make these into zeros. This one was already a 0, so we didn't have to do anything there, but I used a multiple of the first row and subtracted it from the second row to make this one into a 0. My next step would be to establish this as a 1. So I'm trying to do my 1s along the diagonal and 0s elsewhere again. This is already a 1, so I don't need to do anything there. What I would do now is I would take multiples of this row and subtract it from these rows to make this value and this value into zeros. So let me see what I would do next. I would say if I want to take a multiple of this row and subtract it from this row, let's say, so take row 1 minus something times row 2. Well, if I take this 3 minus 3 times this, then I'll get 3 minus 3. And when I assign that back to row 1, essentially this will make this into a 0. So I'm taking 3 minus 3 times this value and assigning it back up here. The reason I'm wanting to make sure I use this row is because you'll notice that this value, so I have to do this to the entire row all at once. I would also, not just do it here, I have to do it over here as well. I'd take, this value minus 3 times that. We'll end up replacing this one. So 1 minus 3 times 0 becomes 1. But you'll notice that actually doesn't change it because there's a 0 there. 3 minus 3 times this becomes a 0, because 3 minus 3 is 0. Here we get 5 minus 6, because again I'm tripling this number. 5 minus 6 is negative 1. And 6 minus 9, tripling this, 6 minus 9 is negative 3. So that's now my first row. 0, 1, 2, 3, 0, negative 5, negative 12, negative 17. That ends up establishing a 0 there. Next off, I would want to establish a 0 here. And what I'm going to do is I'm going to take this value, row 3, well, all the values in this row, but specifically I'm looking at this one, and I want to add some multiple of this one to it to make it so they cancel each other out, or so that they become a 0. So I'm going to take row 3 and add 5 times row 2 to it to become my new row 3. Everything else stays the same. And, well, I guess I shouldn't do that one yet. So I'm going to take my value in row 3 minus 5 times this one. So 0 minus 0 is 0. 5, oh, not minus, plus, but whatever. 5 plus 5 is 0. Negative 12 plus 10, because this one's times 5. Negative 12 plus 10 is negative 2. And negative 17 plus 15 is also negative 2. So now I've created that row and that row. You can see those are shaping up. The next thing I would want to do is I would want to make this into that pivotal one. These are called pivotal ones. So what I'm going to do is I'm going to divide through this row by -2, because -2 divided by -2 will make that into a 1. So I'll say R3 divided by -2 becomes R3. This will give me 1, 0, -3, oops, 1, 0, -1, -3, 0, 1, 2, 3, 0, 0, 1, 1. We're almost done. Now I have a 1 here. Now I'm going to use this to get rid of these two values. And you may have noticed that I'm not changing most of the values when I'm doing this. When I'm doing each of these individual steps, it's a very common thing for people to do these steps kind of simultaneously. So what I'm going to do is I'm going to say make this into a 0 by taking row 1, and well, it's -1. I'm just going to add a 1 to that. So plus row 3 becomes row 1. And in the same step, I'm going to take row 2. Let's see, this is currently a 2. I would want to subtract 2 times this guy. -2 row 3 becomes row 2. I can do both of those in the same step. Since they're not modifying the same thing, it'll just save some paper, or, well, some virtual paper here. So row 2 plus row 3. So 1 plus 0 is 1. Sorry, row 1 plus row 3. 0 plus 0 is 0. -1 plus 1 is 0. -3 plus 1 is -2. Okay. Now what I'll do is row 2 minus 2 times row 3. This one minus 2 times that is 0. This one minus 2 times that is 1. This number minus 2 times that is 0. And 3 minus 2 is 1. And that last row is already set up. So let me just copy it down. And now we have our 1s along the diagonal, 0s elsewhere. We can read this off to read x equals -2, y equals 1, z equals 1. Turns out that this is the one unique solution, so I ended up with the 1s along the diagonal. That's how I know I have exactly one solution here. And -2, 1, 1 is the only solution that satisfies this guy. Let's check it. -2, 1, 1. Let's check this with, it should satisfy all three of those equations. So this is x, y, and z. So this first equation says y plus 2z equals 3. Well, let's see, 1 plus 2 times 1 equals 3. Checking that. 1 plus 2 equals 3. That's a true statement. So it satisfies the first equation. Let's check the second equation. -2x minus 6y minus 10z equals -12. So -2 times -2 plus, or minus rather, minus 6 times 1 minus 10 times 1 equals -12. This is 4 minus 6 minus 10. This should be question mark equals. Question mark equals -12. 4 minus 6 is, what, -2 minus 10 equals -12. That one checks out. And the last equation, 2x plus y minus, so I'm reading it from right up here, 2x plus y minus 2z equals -5. Plugging in the point that I found, -2, 1, 1. Checking to see if this is a true statement. So we get -4 plus 1 minus 2 equals -5. And let's see, this is -3 minus 2 question mark equals -5. That's a true statement. So you can see this point does actually satisfy all three equations that are represented by that augmented matrix.